Oh, wow. It's like a movie director or something, yeah. Oh, do we have chalk or? Oh, some, yeah.
And the
Oh, okay, great, yeah.
Are you going to be here for a while, or are you going to no, just this week. Yeah.
Yeah, well, so it's 50% total, but
so it's okay. I'm called in the fourth here.
Yeah. You're doing a great job. Yeah.
I didn't actually teach it,
So the
so
last couple of weeks,
I
so I think.
So for you it doesn't.
it was kind of a rush.
I was getting really stressed, you know.
No. I was getting 25% for not teaching.
That was a real possibility.
Like the 25% is
This week,
25%. So
longer.
I've done all the ones in the second half.
I mean, they canceled a couple of board games.
No.
It's
It's,
the same as the other board games.
yeah, but it's no. Well, my class is meeting the other day for 2 hours. Yeah, so there's a full I'm a little reluctant that and then I have
but I think it's once students occupy the president. Yes. Yeah. Somehow. The president and the chancellor were away for most of the stuff. The provost was and then they came back immediately. And also they came back. That's occupied. I don't know. Yeah, that might be the reason.
Sorry, I just read over your shoulder. Yeah. Some people wait for the bell. I know. These your notes, or is your notes going to be?
No, my notes are here, but this is just in case I need the time. Because I realized there was no. No, it's okay.
I can give you my watch.
No, it's all right. I can.
And there will be a bell. Okay, so welcome everybody. It's today we have a double header actually. So there's we talk now, and then at 3 there's the algebraic geometry talk. Simon, I forget your last name.
Pepin Lula.
And that's algebraic geometry. People are aware of that, I assume. But, okay. So anyway, now we're very happy to welcome Vicky Hoskins from the Free University of Berlin, and she's going to tell us about group actions on quiver varieties and applications.
Okay, thank you very much for the invite. It's a pleasure to be here. So I'm going to start my talk with a short overview to explain what I'm going to talk about. So the basic object that I'm interested in is a quiver, which is a directed graph, and I'm going to call it Q. So this has vertex set V, arrow set A, and then head and tail maps telling me the direction of these arrows. And then the other thing that we're going to fix is a field K. And then associated to these, one can define certain moduli spaces of representations of the quiver Q over the field K. And these moduli spaces are actually moduli spaces of certain semi-stable quiver representations, and they were constructed by Alistair King. And I'm going to be studying two types of actions on these moduli spaces. So let me call the moduli space MQ for now. So the first action is to consider automorphisms of the quiver and how they induce an action on this moduli space. So I'm going to define precisely what I mean by a quiver automorphism later in the talk. And so this induces certain actions of an automorphism group of Q on these moduli spaces. And the second type of action is to consider, so now we assume that K is a perfect field, and let its algebraic closure be denoted by K bar, then this extension here is Galois, and we can consider the action of the Galois group on the K bar points of this moduli space. So then we're interested in both cases in understanding what the fixed point set are. So describe the fixed locus for these group actions in terms of group cohomology. And so in the second case, for example, we're going to get a description of the rational points of our moduli space over a perfect field. And we're also, so not just to describe them, but so sort of to also give a moduli theoretic interpretation of these. Okay, so let me start properly by explaining what these moduli spaces MQ are. And let me first even explain what a quiver representation is. So a representation of a quiver Q over a field K is given by the following data. So for each vertex in our quiver, we have a K vector space, WV. And for each arrow in our quiver, we have a linear map going from the vector space over the tail of the arrow to the vector space over the head of the arrow. So these are K vector spaces. And these are K linear maps. Oh yeah, sorry. Yeah, this one's, sorry, these are both little, so it's little v in big V. Yeah, and little a in big A. K linear maps. Okay. And there's one invariant of this which we can fix, which is the dimension vector. Which just records the dimensions of all of these vector spaces. Okay. And so you can naturally talk about morphisms between quiver representations and sub-representations and so on. And we're interested in constructing a moduli space for quiver representations up to isomorphism. And this construction, this moduli space is constructed by Alistair King. So using geometric invariant theory. So let me just quickly explain how this is constructed. So one firstly considers an affine space, which I'm going to write as rep QD. So it's a sum over all arrows in my quiver. And then I look at the space of homomorphisms from the standard vector space over the tail arrow. Oh, sorry, I forgot. We should fix a dimension vector D here. So we look at the space of homomorphisms from the standard vector space of this dimension over the tail and to the standard vector space of this dimension over the head of our arrow. So every d-dimensional representation of Q gives us a point in this space by choosing isomorphisms between these vector spaces over each vertex and the standard vector spaces. And then we just need to mod out by this choice of isomorphism. So this is a group GQD. So a product of general linear groups is naturally acting on this space by conjugation. And the idea is that we want to construct a quotient for this action. So so this is just an affine variety. So one thing that you could do is just take the ring of invariance here and then take the associated affine algebraic variety. But this ring of invariance could just be trivial, so we might just get a point, or just the constant function. So instead, what we do is we use a stability parameter, which is just a tuple of integers indexed by the vertices of our quiver. And then this can be used to linearize the action by defining an associated character of the group. So from the group to the multiplicative group of our field. And we use this to linearize the action. Which just means that we lift the action here to the trivial bundle over this, to the trivial line bundle over this space using the character chi theta. Then we get a GIT quotient. So it's a rational map from this original variety to a variety which I'm going to write as MQD theta semi-stable. And this morphism, this rational map is a morphism precisely on an open subset of GIT semi-stable points with respect to this character. So this map here is a so it's invariant for the action of GQD, and it's in fact what's called a good and categorical quotient. So for those of you who haven't seen GIT before, I should say that this double slash notation indicates that this isn't an orbit space in general. So you identify certain orbits whose closures meet in the semi-stable set. Okay. And I'm going to refer to this as the moduli space.
Sorry, could you explain again what this chi theta is?
Oh, it's a character. So this is just a product of general linear groups. Yes. And so the character group of each general linear group is just a copy of Z. And then we sort of weight all of these factors of the determinant by theta. Yeah. So I'm going to call this a moduli space of theta semi-stable representations of Q. So this variety here is actually a K variety. And so why am I now talking about theta semi-stable? Well, in fact, the GIT notion of semi-stability corresponds to a notion of semi-stability which can be defined purely in terms of quiver representations. So we say a K representation W of Q is theta semi-stable if for all sub-representations W prime inside W, we have an inequality of slopes where, so what is this slope? So it's just, we take the a weighted sum of the dimension vectors where the weights are given by a stability parameter. And then we sort of normalize this. Oh, and I should say here that you take all proper non-zero sub-representations. Okay. So since I'm not necessarily assuming that my field is algebraically closed, I have to make a second definition, which is that we say a K representation W is what's called theta geometrically stable if for all field extensions L over K, the L representation W tensored with K over L is theta stable. Oh, and I forgot to say, so stable means that we just consider this inequality with, so it should be strict for stability. Okay. So let me briefly say why I didn't bother to define theta geometrically semi-stable. So in fact, it's equivalent to theta semi-stability because basically because of the existence and uniqueness of the Harder-Narasimhan filtration. Okay, so let me make a few remarks. So firstly, the semi-stable and theta geometrically stable loci are open inside rep QD. So this is all representations which are theta semi-stable and all representations which are theta geometrically stable. And moreover, these quiver-theoretic notions of semi-stability agree with the GIT notions. Okay. Then, so in particular, maybe I should have said, so in fact, sitting inside this semi-stable set is an open subset of GIT stable points for which this good quotient restricts to an orbit space. Okay. And secondly, so this will be very important for the story that we're going to see later, is that if we've got a theta geometrically stable K representation, then, so a bit like stable vector bundles, the automorphism group of this representation is just the multiplicative group. And the stabilizer group of this point, viewed as a space in rep QD, under the natural action of this product of general linear groups, is a very specific subgroup of this group. So namely, it's a group that's isomorphic to the multiplicative group. And so it's just a bunch of scalar copies of the identity, but T an element in a non-zero element in our field. Okay.
So, Vicky, is the space of geometrically stable points a subset of the theta
So yeah, sorry. So we have. So this is a subset here. Yeah. Yeah. Okay. So I think that's all I wanted to say about the background. And now let me explain what I mean by a quiver automorphism. Oh, and I realize I forgot to say this is all joint work with my co-author Florence Schaffhauser. Okay. So let me give the definition of what I mean by a quiver automorphism. So an automorphism of a quiver Q is a pair of automorphisms. So an automorphism of the vertex set and an automorphism of the arrow set, such that we have the following relations. Oh, sorry. And similarly for the head, so basically these two automorphisms commute with the head and tail maps. So technically this is what in our paper we refer to as a covariant automorphism of Q. And there is also a notion of contravariant automorphisms, but for simplicity today I'm just going to talk about the covariant case. And
by saying that the automorphisms of B and A just mean projections, right?
Yes, yeah, they're just finite sets. Yeah. But you just need to assume this compatibility condition. Okay, so then from this you can construct a group, aut Q, of covariant automorphisms. So this is a finite group of automorphisms of Q. And every automorphism in this group determines a functor, which I'm also going to call sigma, I hope it's not too confusing, from the category of k representations of Q to itself, which sends a representation given by a bunch of vector spaces and linear maps to, well, over the vertex V, we just put the vector space corresponding to sigma V, and then we do the same thing with the linear maps. Okay. And you can notice that, so what's the dimension vector of this new quiver representation that we get? So the dimension of sigma of W is just sigma the dimension of W, so which is, which is precisely, I just have the dimension of the vector space over sigma V at each V in V. Okay. So if we want to get an action of some automorphism group on our moduli spaces, and our moduli spaces parameterize quiver representations of dimension D, we need the quiver automorphisms to respect the dimension vector. So for this reason, we consider just a subgroup of the automorphism group of Q. So let capital sigma be a subgroup of the automorphism group, which is compatible with the dimension vector and the stability parameter theta in the following sense. So we have that for all elements of this group, sigma of d is equal to d, and sigma of theta is equal to theta. Then there is an action of the group big sigma. Well, there are two actions. So then there are actions on the affine space rep QD and on the group GQD.
So if the dimensions are all different, then are there any such sigma?
Well, then you could have sigma being the identity, but so no, you need to assume that you pick so if you want, you could pick a group. I mean, you would need to pick a group and a dimension vector which are compatible in this sense. I mean, to get an action. Yeah, exactly. So you have actions given by. So here you've got a bunch of linear maps, and you just send them to the collection of linear maps given by, so you replace the thing over the arrow A by the linear map over sigma A, and the same here. So maybe it's a bit clearer if I write this as a tuple, and here too. Okay. And these are compatible. So let's give these names. So these are compatible in the sense that if with the original action of this group GQD on rep QD, so if I act by some element sigma on G dot phi, then this is the same as first acting by sigma on G, as here, and then using the original group action, acting on the action of sigma on the linear maps, the tuple of linear maps phi. Okay. Okay. So it's quite easy to show that because of these compatibility conditions that we get an action on our moduli space. So let me just, so it's, so the sigma action on rep QD preserves the semi-stable set and the stable set as well, and induces an action on the moduli space. And we would like to understand the fixed points for this action. So let me have a look. Yes, so let me state another proposition which I can then explain a little bit of the proof. So because I mean this is really very simple. I mean it's just you use basically the universal property of the categorical quotient. So the fixed, so to study this fixed locus, we actually use the fixed loci for these two actions here. So the fixed locus G, Q, D, sigma, so this is my notation for the fixed locus, preserves the fixed locus here, And there is a morphism of algebraic varieties, which I'm going to call F sigma, going from, so since this group acts on this fixed locus, we can take the GIT quotient again with respect to our stability parameter theta, and there's a natural map from here to the GIT quotient when I remove these two sigmas, and that's our moduli space MQD theta semi-stable. And in fact, you can check that this lands in the fixed points for the sigma action. So so the idea here is that you show that on this fixed locus rep QD sigma, the GIT semi-stable sets for the group GQD and its fixed locus under the action of sigma agree. And then again, you use the categorical quotient, well, the universal property of the categorical quotient to get such a morphism. Okay. But so let me make a remark about this map. So in fact, you can interpret the domain of this map, F sigma, as a moduli space of representations on the quotient quiver. So domain of F sigma is a moduli space for representations on a quotient quiver, and with respect to a sort of modified d and theta. And so that's the first point. And then the second point is that this map is very far from being a bijection. So F sigma can fail to be injective and surjective. Oh. Okay. So actually, we're going to see that in the Galois setting, this map is always going to be injective, but is not necessarily going to be surjective. And we're going to describe this map using group cohomology. So let me move to the Galois setting for now. So we're going to let K be a perfect field and K bar an algebraic closure of K. Then I'm going to write gal K for the absolute Galois group of this extension, which naturally acts on the K-bar points of the moduli space defined over K. Okay, so the K-bar points of this K variety. And with the fixed locus being the set of rational points. And so the key example to keep in mind, and this was really the motivating example for us, was to consider K being the reals and K bar the complex numbers with the Galois group given by the identity and tau complex conjugation. So we can again interpret this action as being descended from two actions on rep QD and GQD. So this Galois group acts on rep QD and GQD. And now it's maybe a little bit more concrete to see what this is. So if we think of this as just a collection of matrices, then we're just, with entries in K bar, then we're just applying the automorphism to each of these entries. Okay? And the same here, we can also think, so this is just a product of general linear groups. And the analog of the proposition on the bottom right of the board there is the following. So there is a natural injective map, and the key word here is injective, of sets going from, so we take, so we basically take the analogous subsets here. So we take rep QD, and I take the theta geometrically stable points, and then I quotient by, oh sorry, and I take the Galois fixed points, and then we quotient by the Galois fixed points here. And I'm going to call this map F Galois, and it goes to the fixed locus here. Which, as I said, is just the set of rational points. Of moduli space. And what's this left-hand side? Well, here again, we have the top space here that we're quotienting by is the set of theta geometrically stable K representations, and then we're quotienting out by this group which acts as isomorphism. So this is just iso classes of theta geometrically stable K representations of dimension D. Okay, sorry. As a set. Okay, so let me explain the injectivity. And in fact, the very observant people in the audience might have noticed that now I've written theta geometrically stable. And so this will be important because the automorphism groups of those representations is GM, as I mentioned before. So the idea here is, so identify the non-empty fibers of F Galois with, well, something to do with Galois cohomology. So with the kernel of the map going from, so the Galois group of K with coefficients in delta, so remember delta was the stabilizer group of these points, and that's where this really comes in, to the map to H1, so the Galois group of K with values in G, Q, D, oh sorry, there shouldn't be a star here, K bar. Then the point is that this is trivial by Hilbert's 90th problem. And so we see that F Galois is injective. Okay. And in this other case, we can also describe the fibers in terms of group cohomology, whereas now you would replace Galois K with the group sigma. Okay. So let me explain how we give a decomposition of the rational points. So the first thing is that we introduce what we call a type map. Which goes from the rational points of our moduli space to the Brouwer group of our field K, which again we can think of in terms of Galois cohomology. So that's the second Galois cohomology with values in GM. But again, remember that this group is GM, so so we get this coefficient group here, whose fiber over the trivial class in the Brouwer group of K is precisely the image of this map F Galois. So in some ways we want to use this type map to understand all of the points which are in here which don't come from K representation. So this is rational points which don't come from K representations of the quiver. So let me just quickly give the construction of this type map. Or maybe I should check the time and then decide whether I quickly give the construction of the type map. Maybe not. OK, so, well, OK, no, I can give it quickly, but in a stacky sense. So the construction of the type map. So for this, we recall that if we look at the moduli stack of geometrically stable K representations, so this is just the quotient stack. Then this is a GM gerb over the moduli space. So this is just basically saying that every theta geometrically stable representation has automorphism group GM, so the multiplicative group. And so then we just, if we have a rational point here, then we just pull it back, pull back this gerb, and we get a, so if we take the pull back here, we get a GM gerb over K, and this gives us a, so we can also interpret the Brouwer group as classifying GM gerbs over K. So you can also describe it more explicitly in terms of the group actions. The fact again that we have that the image, so the fiber over the trivial class here is the image of F Galois, follows again from a version of Hilbert's 90th theorem. So let me just quickly make a remark that the type map factors via, in fact, the connecting homomorphism for the short exact sequence of groups. Delta is included into GQD, and then let me write it as GQD bar, so the quotient. So it factors via, via this connecting homomorphism. And the way to see this is to note that the GIT quotient, so this map going from rep theta geometrically stable to here, is actually a G bar principal bundle. And so then again, you can pull back this principal bundle, and that's precisely what the points here are corresponding to. So what does this mean for helping us understand the rational points? Well, it means that if we take an element in the image of the type map, then actually it gives us a 1 cocycle here. So which I can just think of as a collection of elements alpha bar tau in G bar QD K bar, and then I can just lift them to GQD. So just choose lifts, which I'm going to call alpha tau, and then this defines, so the family alpha tau determines a modified Galois action in fact, 2 modified Galois actions on rep K bar and G K bar, such that the induced action on the moduli space is the same as the original one, and so then we get an alpha modified version of the map F Galois with the fiber over alpha of the type map is precisely the image of this map, F Galois alpha. So then putting this all together, I can now state our first theorem. So joint with Florent Schaffhauser is that so for K, so assuming one of the conditions here, so K is a perfect field, we have that the rational points of our moduli space decompose over the Brouwer classes in the image of the type map. And then what I need to write here is the domain. So the domains of all of these maps F alpha. So now I take the fixed points with respect to the alpha twisted action of the Galois group, and then I quotient by the Galois fixed points again for the alpha twisted action. Okay, and so this may look a little bit abstract at the moment, but in fact we can interpret this quite nicely, recalling that the Brouwer group classifies division algebras over K. So this is the moduli theoretic description that I promised. So we recall that the Brouwer group classifies division algebras over K. And you can talk about representations of a quiver over a ring or a division algebra. And in fact, linear algebra for division algebras is very similar to just linear algebra over fields. So we have the following result. So a division algebra D lies in the image of the type map T only if the so the index of D, so that's the square root of the dimension of D as a vector space over K divides the dimension vector little d that we started with. So, i.e. D is and then some new tuple, which I'm going to call DD. And then, moreover, we have the following decomposition of our moduli space, well, the rational points. So we take D in the image of the type map, and then we can now reinterpret the sets on the right-hand side using Galois descent. So they are theta geometrically stable representations of Q over the division algebra D of dimension DD up to isomorphism as representations over D. Okay, and let me just give an example in the reals case. So if K is the reals, then the Brouwer group of K has just two elements, so the reals and the quaternions. And then we see that the real points of the moduli space correspond to either real representations of Q or quaternionic representations. And the second type, these only occur if 2 divides the dimension vector. So because the quaternions have dimension 4 over the reals, and then we take the square root. Okay. And so let me briefly summarize what happens for quiver automorphisms. So for quiver automorphisms, there is a similar decomposition, but it's much more complicated because we don't have Hilbert's 90th theorem. And we can interpret, so the modular interpretation this time is in terms of certain equivariant quiver representations. And we give an application to the construction of branes in certain hyperkähler quiver varieties. Okay, and so the bell has gone, so I will stop here. So thank you very much.
So how does this depend on theta?
Well, so the Galois story doesn't depend at all on theta, but obviously in the quiver automorphism case, you need theta to satisfy this compatibility condition with the group that you're acting on. So, but there are many examples. So, for example, like the star-shaped quiver, which is related to moduli space of vector bundles and Higgs bundles. I mean, there are many. So there are many thetas for which you can study interesting actions. So because then in the star-shaped quiver picture where you have n outer vertices and an inner one, you have a natural action of Sn on this, and you can produce interesting branes and things like this from studying these actions.
All right, thanks again. So we will